Okay, today we're going to start gas laws and usually introduce those with Boyle's law, Charles' law. Normally don't need to memorize the names, but do want to be familiar with the formula. And that formula is right here for the first one, which is Boyle's law. And really it's pressure and volume and kind of how those things interact. So let's just talk about that real quick. Basically, if you kind of think about it, you have a container. And so let's say you have this container, and we'll draw just a quick little box. So you've got a container. And in that container, you're going to have some gas particles. Now, what happens is that the amount of particles in there are the same. So we'll say that there are 3 particles in there. 1, 2, 3. There's 3 particles. And they're moving around. They're bouncing off the walls of your box. And the box is sealed, so they can't get out. So then you take the box and you just make it smaller. So it's the same particles. They're just, now you've squeezed the box and you've made it smaller. So there's our box. And we just now got this smaller box, but our same 3 particles are still in there. So what are the particles doing in the box? Well, they're basically just bouncing off the walls. And when they bounce off the walls, we call that pressure. But now look, see the same 3 particles are in this much smaller box. So what happens is that if I took the volume, and again, volume is the space, right? So this is my volume. And I made the volume significantly smaller. So my volume went down. If I make the volume smaller, what happens is that those particles are going to bounce around, but they're going to hit the walls quite a bit, with quite a bit more frequency. They're going to hit the walls a lot more. So since I made the volume go down, the pressure ends up increasing, because what happens is that those particles are going to bounce around and they're going to hit the walls quite a few more times. And so if you kind of think about the motion in here, it's going to be a lot more than in here. And so there's going to be more collisions over here. So pressure goes up. So what we want to kind of think about here is the idea that if I made the volume smaller, kept the same 3 particles, the pressure goes up. So what we want to think about is the relationship here is basically that these are going to be opposites. And you might want to write that down, that this is going to be an opposite relationship, or they're going to be indirect. So basically, one goes up, the other goes down. So let's make a simple graph of that. So for number 2, make a little bit better one there. Let's make a simple graph. So we're just going to have pressure, and we're going to have volume. And so let's think about this. If our pressure is high, then the volume has to be low. And so then we're going to kind of have a spot there. And if the pressure is low, then the volume is high. And then it just sort of plays out something like that. And so that's sort of the relationship you're going to see between pressure and volume. They're going to go in opposite directions. So now we're down here with STP, standard temperature and pressure. So you're going to see this a lot, STP. It gives you some choices. Standard temperature is going to be 273 Kelvin. So if you have standard, and then that's standard temp, so the temp first. So our standard temperature is going to be 0 degrees Celsius, or, and this is what you're going to use most of the time, 273 Kelvin. We use Kelvin a lot in gas laws, so this is what you're going to probably be using, is the 273 Kelvin. Now the standard pressure, put that one down here because I don't have a ton of space. You guys can put it in the correct area. But the standard pressure, you have 2 choices. It's going to be 1 ATM, that stands for atmospheres, or 760 little m, capital H, little g, millimeters of mercury. So those are kind of your options that you have to work with. I often pick the ATMs if possible because math is easy with ones, but sometimes you're kind of forced to use the millimeters of mercury. So, all right, we're gonna do a problem now, and we're gonna work problem 4. So I'm gonna clean this up and then we'll do that problem. Okay, we're gonna work problem 4 right here. And first thing is that I really like you to write down the variables, and so we know that we're going to be working with this formula, Boyle's law. So when I do a problem, I write down pressure equals volume equals, and those can be the ones, and then I do pressure equals volume equals, and those can be the twos. Now you might want to have a little, you might want to not use as much space as I'm using, but I'm just doing that so I can show you what's going on. And so the ones and the twos really don't mean anything. It's just that if something has a volume at a certain pressure, they need to go together. So these are technically the ones and these are technically the twos, but that doesn't matter that much. So if you read the problem, it says a sample of oxygen is at 720 millimeters of mercury. So that is a pressure. And then it says, and it has a volume of 150 milliliters. So those go together. So these need to be either the ones or the twos. It doesn't matter. I'm going to go ahead and just make them the ones, but you could make them the twos just as easily. It doesn't matter. So my pressure is going to go right here. That's going to be my 720. And you'll notice the unit's going to be important because I got to have the same unit on both sides. And then this value is my volume. So I'm going to drop that in here, 150 milliliters. And so what happens is we finish reading the problem, and now it says, what's the volume at standard pressure? So those two go together. So the yellow ones went together, and the green ones go together. So they want to know volume, so I'm going to go ahead and put an X here. And standard pressure. So remember, we had choices for pressure. It was standard was either 1 atmosphere or ATM. The other option was 760 millimeters of mercury. The same exact value, just different units. Well, we want to pick this one because it matches up with the units that we already have. So we're going to come down here and we're going to go ahead and drop in a 760 millimeters of mercury. There you go. Now you got a problem. All right, so I'm kind of running out of space, so I'm going to drop it down here on number 5. So it'd be 720 multiplied by 150 equals 760 times x. So we're going to solve for x. I want the x by itself. And so I don't know if you remember your algebra too well or not, but basically you would just, the way it works is you divide both sides by 760 in order to get the x by itself, and those end up canceling. And so what it looks like is you always divide by the number that's with the x. So if you think about it that way, it would be x equals the 720 multiplied by the 150 divided by 760. Now you're always going to end up doing the same thing where you're going to end up dividing by the value that was sitting next to the x. That's just algebra. You need to get the x by itself. So 720 times 150 divided by 60. Now I already know from initially what we talked about up here at the very beginning. We said, hey, if I change one value, the other value is going to go in the opposite direction. So what did we change? Well, we went from 720 as a pressure to 760. So that went up. So we know that we're going to go from 150 to x. We know x should go down because, see, remember, these are opposites. So our answer could be correct if it goes down. Okay? So just run through your calculator, 720 times 150 divided by 760. And if you run all that through, I ended up getting, kind of run out of space here, I ended up getting an answer of 142. And 142 what? Well, it'll be the same unit. So that's milliliters, so it'd be 142 milliliters. And so that's what you get. Makes sense, because if you look 150 to 142, our value went down, and that's what was supposed to happen. So, all right, that gives you a pretty good look at Boyle's law. And so we're going to take a quick look at Charles' law, which is on the next page. Okay, main thing with the Charles law, you'll notice, is when you're looking at the formula, you've got volume and temperature. And of course, we're going to have to deal with fractions, numerators, denominators. But the way this is going to work is that basically if you increase temperature, so say you have a balloon and you increase the temperature of said balloon, what happens is the particles are going to move a lot faster and they're going to spread out. And they're going to make the space inside that balloon a bit bigger. And of course, if it's cold, they would contract, they would not move as much, and then the balloon would be smaller. So basically, volume and temperature are going to be going in the same direction. So this is a direct relationship. So the graph for this direct relationship, they both go up or they both go down. If you do a quick graph here, if volume is high, then temperature is going to also be high, and if volume is low, temperature is going to be low. So you get a direct relationship here. And so this one is a pretty straightforward. One goes up, the other goes up, one goes down, the other goes down. So that's going to be something that we'll look at as we look at these problems. Both go in the same direction. Okay, very, very, very important, probably one of the most important things we're looking at today is that you have to convert your temperature into Kelvin for gas law problems. It does not work ever in Celsius. And so what you do is you just take whatever you have in Celsius, so your degrees Celsius, and you just add 273, and that will give you Kelvin. But you must do this on any value that has Celsius, or the answer is going to be incorrect. And again, probably the most important thing that I can show you today is this, because it's going to come up a lot. Some teachers have you do a more specific value with a decimal, but we're just going to do Celsius plus 273. So we're going to work real quick number 13, and I'm going to clean this up, but we're going to work 13 and kind of see how that looks, because again, just an algebra problem. So okay, so set this up ahead of time, clean this up a bit. And so we've got volume, temperature, which of course is our formula. So what you want to do is you just want to go through and you want to put all those values in. So we've got 2 liters and it's at 27 degrees Celsius. So we're going to go ahead and for the volume, we're going to put in our 2 liters, but then we're going to do 27 plus 273 because we want to convert it into Kelvin. So you just want to make sure that you're converting into Kelvin. And it says that we're looking for volume at 42 degrees. So I'm going to do the same thing with 42. So 42 plus 273, that's going to equal 315. And so this is a 315 Kelvin, and this is the X. So we're just going to set that up and solve for X. All right, to save some time, it's kind of running out of time here, I put the formula up there. So we're going to cross multiply and divide. So what that means is we're going to multiply where the X is not. So multiply these two, and then we'll divide by 300. So we get that set up real quick. All right, so I'm kind of running out of time on this 15-minute video, so I went and put the formula up here, and then I went ahead and did the cross multiply and divide. So again, I multiplied where the X was not, so 2 times 315, and then I divided by the other number. So over here, there it is, 2 multiplied by 315 divided by 300. So you multiply where the X is not, cross multiply. Then you end up dividing, and you end up with a final answer of 2.1 liters. And so it's going to spit out an answer in liters because we start with liters. So that should get you going. Should be able to run through the practice on this, but that should set you up for Boyle's and Charles' law.